What's up, everyone? I'm Jacob, and this is Archimedes Tub. And today we are going to be discussing aluminum because for some reason I've kind of developed an obsession with aluminum. I don't know why. I guess it's just like, it's so easy for people to access, really. Aluminum foil, aluminum cans. Go dig in a trash can or recycling bin, find plenty of aluminum. There's no shortage of it. And yeah, and it's pretty interesting to work with. I've worked with it doing like electrolysis stuff, trying to like make an aluminum oxide, and actually made an aluminum oxide sol gel in one of my previous videos. You can go on the channel and go a few videos back and it'll be there. And then a couple of weeks ago, I was researching on the reaction between aluminum oxide and ethanol, because I was wondering if it could form diethyl ether. And I ended up stumbling across this article that you see on the screen here titled "Gelatin Template Synthesis of Aluminum Oxide and or Silicon Oxide Containing Micro/Mesopores Using the Proteolytic Sol Gel Method." And essentially what they did here was very similar to what I did in my sol gel video, except they have a different end goal here, because what they're trying to do in this paper is create the sol gel holding the aluminum oxide and then calcining it at, I believe it was 700 degrees. And essentially what this will do is it'll burn off the gelatin and it'll leave like porous crystal aluminum oxide, and in these pores are like the reaction sites to, in this case, according to the paper, produces diethyl ether as well as ethylene, if I'm not mistaken. Let's scroll down here some. Don't worry, we'll come back to this. But I just want to find this chart quick. Yeah, this one here. And so basically what we're seeing here is charts. This one here represents, like, in the paper they did different mixtures of, like, one was just like straight up aluminum, the other was a silicone aluminum blend, 1-to-1 ratio. Then another one was one silicone to 2 aluminum blend, and then a 2 silicone to 1 aluminum blend. And in this chart here, we can see that the y-axis represents our ethanol conversion percentage, and the 2 silicone to 1 aluminum ratio had the highest rate of ethanol conversion, around 48%. And if we look on this chart at the top right, we can see the conversion percent based off the surface area in meters squared per gram on our y-axis here. And see, once again, the 2 silicone to 1 aluminum ratio has a greater conversion percentage once again. However, it's interesting, like, because this graph here talks about the surface area, and we can see, like, based on surface area, the silicone aluminum 1-to-1 blend has the same conversion rate as the aluminum, strictly aluminum blend, based on their surface area and meters squared per gram. But on this upper left-hand chart, just by the conversion percentage, aluminum compared to the silicon aluminum 1-to-1 blend is just way less. So that's a pretty interesting thing to note here. And we look at this bottom chart here where we have selectivity on the y-axis and different blends labeled on the x-axis. And we can see that a lot of all the blends that contain silicone tend to favor diethyl ether production rather than ethylene, with the 1-to-1 silicon aluminum blend showing the greatest selectivity for diethyl ether at about 70%, with ethylene being produced at about 30%. And then, for the aluminum, strictly aluminum blend, you see more of a ethylene production, which matches up with other stuff I've read in the literature. This is pretty interesting, seeing that play out again. But yeah, basically, from what I remember reading this article, it's possible if there was like a basic reaction site. Here it is, alcohol dehydrogenation to produce acetaldehyde using basic sites. Thus, the different supports were tested in ethanol conversion to determine the acidic strength order of the solids. So we can see that no aldehyde was produced at all. Thus, there aren't any basic sites present for it to react, or at least in a significant amount. Let's see here. Yeah, here they say, talking about the dehydration rate of the ethanol, it's directly related to the acid strength, which of course makes sense. And in this case, the order of the acid strength was 2 silicon to 1 aluminum blend is greater than the silicon to 2 aluminum blend, which is greater than or stronger than the silicon aluminum blend, which is stronger than the aluminum alone. And aluminum oxide, I believe, is a amphoteric molecule, meaning it can act as both a base and an acid, which kind of makes sense as to why it's further down towards the list as being a strong gas, as like in comparison, like strength comparison to the silicon aluminum blends. Yeah, let's go back up to the top here and just kind of start from the beginning. So yeah, so an introduction of this basically talks about catalytic supports. Let's see what they here. So then here, in general, supports are used since they allow obtaining a high specific surface area. Let me start from the beginning. Catalytic supports are an important class of materials which, as their name implies, fix the active sites on the solid surface in order to improve their different physiochemical properties. Let's define physiochemical properties. So physiochemical properties can be classified as molecular properties such as molecular weight, dipole moment, polarizability, van der Waals, volume, and surface area, as well as bulk properties such as acidic or basic character in solution, octanol or water, partition coefficient, solubility, etc. So yeah, in general, supports are used since they allow obtaining a high specific surface area to lead to adequate porosity, provide appropriate acidity and or basicity, and tolerate elevated temperatures without suffering significant degradation, which means they have a high thermal conductivity. Now, so these different characteristics influence how a catalytic substance performs in a reaction. And it says here, the literature reports various methods for preparation of catalytic supports, such as conventional sol gel, polymeric precursor, hybrid spheres, and co-precipitation. Saying many of these existing techniques have considerable cost and take significant time, and typically use precursors from non-renewable sources compared to the protease sol gel route proposed here, which uses gelatin from porcine skin as organic precursor, and aluminum nitrate and or tethoyl orthosisylate as inorganic precursors. Now, when I made my sol gel, I did it a little differently. I used just like straight up aluminum oxide. Didn't have aluminum nitrate or tetraorthosisylate or silicate. I don't know how much of a difference that makes. As far as like after one were to burn off the gelatin and to leave the crystals there, I'm not sure if it would act as a catalyst as effectively as with the method they're doing, but I feel like it should to an extent, you know. It says here, the synthesis of porous supported materials with potential applications in catalysis still need to be studied from the gelatin precursor. And then it goes on to define gelatin as a partially hydrolyzed collagen, where the basic unit comprises a protein chain of about 1,050 amino acids. Goes into the composition of gelatin. However, its application as an organic precursor, biotemplate, and the synthesis of porous catalyst remains an open research theme. It is important to emphasize that the functional groups of the gelatin may act as an excellent complexing agent of the metallic cations, such as aluminum 3+ or silicon 4+, which is very interesting during the synthesis of metal oxide catalyst with high metallic dispersion and porosity. Soria et al. Reported that the annual world output of gelatin increased to 326,000 tons. Okay, anyway, moving on from that. The use of the organic precursors in the synthesis of catalyst as gelatin allows having some control over the metallic dispersion, morphology, and particle size, and directly affects the textural, morphological, and structural properties of the final material, which are essential characteristics in the efficiency of the catalytic process. So that answers that. Thus, the present work shows that the bio-inspired synthesis and characterization of catalytic supports containing aluminum oxide and or silicone using an alternative synthetic methodology from gelatin, which is efficient and of low cost. So in the experimental section, we talk about getting into support preparation. 5 samples were put together, denoted by 2 silicon, 1 aluminum, 1 silicon, 2 aluminum, 1 silicon, 1 aluminum, and silicone. Was performed by the protease sol gel method using porcine gelatin as organo-soluble precursor. And I'm pretty sure when I did mine I used beef gelatin, but I doubt it matters too much. The numbers, of course, representing the molar ratios between aluminum and silicone. So yeah, so aluminum, straight up aluminum oxide, showed like some of the lowest conversion rates from what we saw on the chart earlier. Let's see. Okay, so it said the different solids were prepared based on the different steps in the flow chart in Figure 2. For all samples, the required mass of gelatin in distilled water was first dissolved in a beaker under constant agitation, and the appropriate mass of aluminum nitrate and/or tetraethyl orthosilicate was concomitantly dissolved using a magnetic stir. After that, the inorganic solutions were added to the gelatin in order to drive the complexation process and the formation of zerogel. I'm not sure how you pronounce that word there. Let's find out. Okay, yeah, it is with a Z. Zerogel. Okay, cool. So zerogel. The ratio by weight between the organic and inorganic was maintained at 1:1 for the various samples. Interesting. Okay, so let's see here how they proceed. Subsequently, the formed aerogel, as a result of the interaction between the organic and inorganic material, was kept at 110 degrees Celsius in an oven for 2 days to dry the samples. Finally, after being removed from the oven, the dried samples were macerated, placed in a porcelain crucible, and calcined at 700 degrees Celsius for 2 hours in a muffle furnace. Stuff about analyzing the supports. Always show, not tell. So this is the structure of gelatin here. As you can see, there's a lot of different sites where reactions can take place. Like I mentioned earlier, sequestering aluminum and silicon ions. And here's the flow chart that I mentioned earlier, discussing the synthesis of the proteate gel. We see here what they start on one branch. You start with distilled water and gelatin, transfer that into tetraethyl orthosilicate, and then that turns into the aluminum silicone gelatin solution, which turns into the zerogel, dry, maceration, calcination. I don't know what maceration is. Let's look that up too. One of the simplest extraction techniques in which coarse and powdered plant material is soaked in solvents. So popular. Oh. Okay. Sure. Result in discussion. Thermogravimetric analysis show the weight loss with increase in temperature. The 3 major regions of the weight loss were observed, except for the pure silicon support, which showed only 2 regions. The first region, between 30 and 150 degrees Celsius, shows the loss of physisorbed water. Blah, blah, blah. so on and so forth. Finally, after 600 degrees Celsius, this leads to the formation of aluminum oxide and or silicon oxide with high porosity due to the cavities created by the absence of gelatin, which was also evidenced by the color change comparing the obtained samples after drying after calcination. Thus, all samples were calcined at 700 degrees to ensure the complete release of the organic matter and formation of the metal oxides, aluminum oxide, and silicon oxide. Then go to X-ray diffraction, FTIR. Let's see what it's saying here. Okay. Specifically for sample silicon, the second third range occurs at single events between 250 and 530 degrees Celsius, indicating that the presence of aluminum nitrate causes changes in thermal decomposition properties. Since aluminum nitrate and silicon and TiOS interact differently with the functional groups present in the gelatin, the complete elimination of the organic matter occurs at approximately 600 degrees Celsius, indicating that this is the minimum temperature required for complete decomposition / oxidation of the organic and inorganic material. So comparing the attained values of stresses for samples after drying with the pure gelatin, a variation of wave number and band intensity for solid after complexation, zero gel formation related to the original gelatin was noted, probably indicating that the metals, aluminum, silicon, were complex with the functional groups of the gelatin. This piece of information confirms that the formation of a hybrid material during the first stage of synthesis. The uniform dispersion of the metal ions in the gelatin radicals due to the complexation in specific positions. Functional groups of gelatin is essential to obtain a widely dispersed metal oxide after calcination, as observed by the X-ray diffraction. Let's see which ones. Here's the scanning electron microscopy images. You see different pores here. I'm going to zoom in a little more. Yeah, pretty interesting stuff. See if we can get to more of the good stuff here. Let's hop into 3.6 here, acidity from ethanol dehydration. Characterization of the catalyst by model reactions is rather common to evaluate acid-basic site strength. The alcohol's decomposition is a model reaction to determine the acid-base nature of catalytic materials. It has been reported in the literature that the ethanol decomposition reaction can follow three possible routes: intramolecular dehydration that produces ethylene using acid sites, which we know occurs in aluminum when you mix ethanol and aluminum oxide together. There's other literature that confirms that. Intermolecular dehydration to generate diethyl ether from acid sites, and alcohol dehydrogenation to produce acetaldehyde using basic sites. Thus, the different supports were tested in ethanol conversion to determine the acidic strength order of the solids. In the first few minutes of reaction, all active sites are available for ethanol absorption, thus the first points are more representative of the total acidity. The selectivity results confirm the presence of acid sites, since only dehydration products, which would be the ethylene and diethyl ether, were observed. The presence of basic sites was not identified, since the ethanol dehydration product, acetaldehyde, was not observed. Says here the higher selectivity for diethyl ether is justified by thermodynamic aspects, considering that the ethanol dehydration to diethyl ether is an exothermic process, which is favored at low temperatures. 250 C. Is favored at low temperatures, 250 C. Greater selectivity to diethyl ether is expected compared to ethylene, which is an endothermic reaction. Diethyl ether is found very predominant at low temperature and conversion, while ethylene is predominant at high temperature and conversion. And if you've ever made diethyl ether from scratch, you can definitely tell it's an exothermic reaction when you mix the sulfuric acid and ethanol. Let's see here. Considering that the dehydration rate is directly related to acidic strength, the solids had the following order of acid strength: 2 silicon, 1 aluminum, silicon, 2 aluminum, silicon, aluminum, and aluminum, which is directly related to silicon aluminum ratio. And we saw that in this chart here. In the case of alumina, an amorphous silica and amorphous silica aluminas, the acidity trend is closely related to the surface area. The higher the surface area, the higher catalytic activity, which we see in this chart here. Let's look at this figure here. Gelatin and organic precursors, where M can be silicon in the 4th oxidation state or aluminum in the 3rd oxidation state. This results in hybrid materials, gelatin and metallic cations. And then calcination at 700 degrees Celsius results in the elimination of gelatin, leaving only the metal oxide behind. Let's see here. The gelatin method leads to the formation of acidic supports where the strength depends on the silicon-aluminum ratio. So if you go on the gelatin route, use silicon-aluminum ratios, mixes. The essential role of gelatin in the formation of micro/mesopores with a high dispersion of metal oxides is illustrated in the schema figure 9, which was that one there. The potential complexing functional groups of the gelatin, amino and carboxylic acid, are responsible for the complexation of metal cations, aluminum 3+ and or silicon 4+, leading to a uniform dispersion of metal cations in the organic matrix, the gelatin. The higher dispersion is maintained for the metal oxide, even after calcinations, and concomitantly the formation of nanocrystallites with very small size occurs, since the organic template acts hindering the centering/coalescence of the particles in organic fractions during the calcination stage. The formation of mesospores of silicon oxide and or aluminum oxide is justified by the morphology, which is spongy-like, and the texture, which has a high porosity, the starting template, gelatin, which are replicated in the hybrid material, the zero gel, and subsequently in the final oxide, silicon oxide or aluminum oxide after calcinations. Similar polymer template synthesis mechanisms. A porous oxide was previously described with other templates. Conclusions. The catalytic supports containing aluminum oxide and or silicon oxide or synthesized through an alternative method denominated proteic salt gel, which uses an organic precursor template, the gel, in this case the gelatin from porcine skin, not person skin, porcine. These supports have low cost, are simple, and have efficient methodology beside using an organic precursor from a renewable source, which may be characterized as an environmentally friendly synthesis, i.e. green chemistry or sustainable chemistry. Teaching analysis show different mass loss regions, This basically just sums it up. The model ethanol dehydration reaction confirmed the presence of acidic sites and indicated that the acid strength increases with increasing the silicon-aluminum ratio. The presence of basic sites was not identified since ethanol dehydrogenation product was not observed. Thus, the study indicates that the synthesis method used from gelatin is interesting for catalytic supports preparation containing aluminum oxide and or silicon oxide, since it presented promising structural, textural, morphological, and acidic properties which are essential in applications such as heterogeneous catalyst. So yeah, that's a brief summary of that paper. Yeah, I've definitely got more aluminum papers I can go through and discuss at a later date. I think call this series the Aluminum Files. Yeah, aluminum, very, very interesting metal. Something I definitely intend to keep working with in the future, in whatever ways I can. But yeah, I hope you enjoyed this little discussion. Should definitely look up that paper. Once again, the title is Gelatin Template Synthesis of Aluminum Oxide and or Silicon Oxide containing micro/mesopores using the proteic sol gel method. And these are the authors here. I'm not gonna try butchering their names, but all credit to them for this research. Yeah, so I hope you enjoyed the stream. Feel free to tune in to the next stream whenever that may be. And have a good one, and hit that like and subscribe button if you don't mind.